Hey guys, it's Dr. Calkins. So today we're going to do experiment 16 to precipitate or not to precipitate. Double replacement reactions. Again, two partners, and they switch. Positive doesn't like positive, negative doesn't like negative. Like we saw in the other videos and we see in the lecture. As we use this, we're going to definitely get some practice on the solubility table, which will be a major component of our homework and then eventually our exam. You get to use this on your exam, so just be familiar with how it works. Remember the yellows, they're also in this lower category. We'll talk about it in the other video as well. But those ones that are in yellow, those are the ones that never, ever, ever precipitate, no exceptions whatsoever. We would call those the designated drivers. They're never going to contribute to a precipitate ever. They will always, however, be spectator ions. Everything else is something you have to worry about. So it's really this diagonal here. That diagonal is the ones that never precipitate, they're spectators, they're soluble. And it's this opposite diagonal that we have to watch out for when we look for precipitates or water insoluble. So again, it's either precipitates or the spectator ions. So that's the idea of how to look at that table. So we're going to flip over and do some practice. Here's a warm-up of how it's going to look, much like our video from before. We're going to put things into a well plate, they're going to separate, and then we add something else to them, and as that one also separates, they can trade partners. And when that trading partnership happens, we do have spectator ions, and again, sodium and nitrate are the ones in yellow on the other page that are great examples of those designated driver spectator ions that never do anything. But again, iodide does have an exception, lead, silver, mercury, and here's lead, and it's going to produce a yellow color. So our lab is basically working through a bunch of examples like these. Lead nitrate, PbNO3, cross the 2, cross the 1. Sodium iodide, Na and I. No charges there to cross, plus 1, negative 1 cancel. Double switch, lead goes with I, sodium goes with nitrate. Remember, lead's still a 2, so we have to cross the 2, cross the 1. We did balance it because 2 sodiums, I. We needed 2 I's because we had 2 I's and it was lead. And then, again, because sodium and nitrate were in yellow, they're going to be the spectator ions that we're going to list below. As we do this lab, we're going to see precipitate colors, and we're going to fill that out as we show and demonstrate that. But we're going to circle who's producing that color in some of that busy work. So let's try some busy work together real quick. We'll give you a chance to get that done, and then you'll be able to pause the video and then eventually get to more examples of what they actually look like. So I'm going to walk through a few of these just to get you a head start. So lead nitrate and potassium dichromate are what we need to mix together in lab here in a few minutes. So we're going to take lead, which is Pb, and when you watch the video, if you look at it slowly, you'll see all the answers for all these compounds on the bottles. The lead is a +2, nitrate's a -1. So cross the 2, cross the 1. We're going to add it to potassium, which is K+, chromate, which is CrO4, -2, so bring that 2 back over. Double replacement says double switch, so leads and potassium switch. We're going to have a K with now nitrate. Doesn't really matter who you write first or second here. And then in the end, we're going to have lead with whatever's left over, and that's going to be chromate. We should know something already, and that's that potassium and nitrate are in the yellow. They're the ones that are always water soluble here, and water soluble here. Scientists use those because they know they're going to behave. By using something that we know behaves, we don't have to worry about a reaction before the reaction we want actually happens. So there's our spectator ions. K+ is never really going to hang out with nitrate. They're both going to be floating around in solution as spectator ions. So in this lab, if we see something produce color, we know it's lead chromate. And if you look at our lab book for chromates down at the bottom, you're going to see pretty quickly in that category of chromates, chromates are always precipitates. The only time they're not precipitates is when they're with silver, lead, lithium, sodium, potassium, and they were with potassium. But when they took them to the party, it's like that combination gives us that color change precipitate, and we'll see that color in lab. Let's flip over a page and show you one. Same kind of idea. Copper sulfate, barium nitrate. So we have a copper 2, sulfate is a -2. Barium and nitrate, that's a Ba. Nitrate is a -1. Barium is a +2, so cross the 1, cross the 2. Double switch. Coppers and bariums trade, so copper now with nitrate, and again it doesn't really matter here who goes first or second. Cross the 2 still, remember it's a 2. And then also over here we have what's left over, and that's the barium and the sulfate. So identify anything in the yellow category. That's what we do first. One of the first things you should find is nitrates. Always love water, no matter what. Always spectators. So now with copper, we know that those are going to behave. So what we're worried about is what the heck is barium and sulfate going to do? Let's go back to our little table. Check out sulfates. Sulfates are in this category of usually being behaved. Kind of like this party idea. Sometimes when you grow up, you have these old flames from high school. So when you go to a party for the first time in a long time, you might see one of those old flames from high school and recognize they're going to get you into trouble, just like I did in the past. So watch out for lead, calcium, barium, and strontium if you're sulfate. And if we go back to our example, there's one of those crazy ex-boyfriends or girlfriends that we're worried about. There's our solid. And if we see that color, and we will, these are the ones that we'd circle. I'm not sure if we circled that one on the other page, but again, precipitates are circled in the end. So again, that one there would have gotten circled. I just skipped that step. One more example, and then we'll get to lab. Plenty for you to practice outside of that. This one a little bit quicker. Sodium and iodide, Na plus and I negative. Silver nitrate, silver plus and nitrate negative. Double switch, sodiums and silver switch, kind of like changing last names. We have a Na and now an NO3, and we have an Ag left over with an I. So again, look for those in those yellow positions. You're going to see pretty quickly group 1 metal, so aqueous. You're going to see nitrate, aqueous. But notice now they're together because they should be, they're the spectators. They never do anything wrong, ever. Always water soluble, always spectators, no matter what. So if something happens in this reaction, it's because of silver and iodide. Let's look at iodide. Sure enough, iodide is very well behaved usually. However, it does have some crazy exits from the good old days that we have to watch out for because they will precipitate if they get together. Lead, silver, and mercury. Let's go back. Do we see lead, silver, and mercury? And sure enough, we do. So when that happens, we form a solid, which we'll see in lab. And now we know who's producing that solid. So we circle it. Lots of busy work, and that's your time, or at least your turn, to do it now. All right, here we are with our first one. We have some lead nitrate and potassium chromate. So if you look at our bottles, we have them starting with silver nitrate, A in the alphabet, all the way across, aluminum sulfate, barium chloride, barium nitrate, barium hydroxide, cobalt chloride, copper sulfate, iron chloride, potassium bromide, potassium chromate, potassium dichromate, potassium iodide, sodium chloride, sodium iodide, NaOH, which is sodium hydroxide, sodium sulfate, ammonium chloride, nickel chloride, and then finally lead nitrate with the letter P. So what we're going to do is take a couple drops of each one and see what we make. So we need to find our lead nitrate all the way here at the end. I'm going to take it to our first little well and give it a squirt. And then now we need potassium chromate from our yellow bottle and put it in and see what happens. Record your observation. Going to do the same thing again with lead nitrate once more. And now with potassium dichromate, watch for observations. There's our color. Now we have lead nitrate again. potassium iodide. Watch for observations. We're up to barium chloride. And we need potassium chromate. A little paler yellow there. And lastly, for this page, we need a sodium sulfate. And barium chloride. We get a white there. So take a few minutes to record your observations. Don't forget the busy work, and don't forget to balance equations. We didn't do that, and I didn't do that on purpose. So don't forget to balance, and we're going to flip over to the next page. We're back for our second row. We're going to take some copper sulfate. And now some barium nitrate, and see what happens. Number 7 is aluminum sulfate. And now barium nitrate. Next we have number 8, sodium chloride, so some salt water. And some silver nitrate. This is a chemical cauterizer. They put it around things like Mickey buttons and stuff, so it's not good for your hands. It likes to make your skin stop growing, at least for a few weeks. Number 9, potassium bromide. And now silver nitrate again. One of those crazy ex-boyfriends coming up, and exactly what we'd expect. Silvers and lead's bad for that. Lastly, we have potassium bromide. And ammonium chloride. 2 clear solutions. And notice nothing happens. So sometimes double replacement reactions don't work, and that's because everybody is a spectator here in number 10. So take a few minutes to record your observations, and then we'll move on to the next page. All right, we're back for now page 3 of our precipitates. We have sodium iodide. We need silver nitrate. You can probably expect what's going to happen next. We have iron 3 chloride. And now barium hydroxide. Hydroxides aren't well behaved. And now we have cobalt 2 chloride. And barium hydroxide again. Barium is one of the few hydroxides that's well behaved, and notice when it's not with barium, things tend to happen. Nickel 2 chloride. And sodium hydroxide. Lastly, copper 2 chloride. And finally, sodium hydroxide. So take a minute to record your observations. Looks like the only no reaction was this one from the previous page. Everybody else produced a precipitate, as hopefully your busy work has shown. All right, so we're back on now page 110. We said in the other lecture that neutralization is just a fancy type of double replacement between acids and bases. So very similar to the busy work we saw earlier, we're going to do the exact same thing. We're going to be looking for the acids, looking for the bases, looking to mix them together and then make water. Notice sodium chloride. Sodium always a spectator, so it's going to bring chloride with it as a spectator ion. And now we're not looking for a color change like we saw earlier. Instead, we're looking for water to form, which we can't see, but we can feel it, so these tend to get very hot. And sometimes so hot that we can actually hear them sizzle, as we'll see in lab a little bit later. Let's try one example, give you an idea how to attempt the busy work in this page. Remember, my ride has hydraulics, so there's your hydroic acid. So that's a hydrogen chloride, H plus Cl negative. We have calcium hydroxide. Calcium is a group 2 plus 2. We have hydroxide, which is a negative 1, so cross the 1 across the 2. Switch. Calcium's and hydrogen, so now we have calcium and chloride, so again, cross that 2, cross that 1. Remember, we're going to write water as HOH. That reminds you of how it doubly replaced. And that's going to be important for later. We need to figure out who's water soluble, but remember, chlorides, as long as we're not with silver, lead, or mercury, we're fine. So aqueous, and still aqueous, no silver, lead, or mercury around. So there's your spectators. In this case, plus 2 and negative 1, we don't need that one. Calcium and chloride are our spectators there. And water, again, is our liquid. So circle it as you will on the rest on this page. So we're going to go over to lab and do a few examples. All right, so we're back for our last page. We need some hydrochloric acid and some calcium hydroxide. So we're going to take this very nasty eat cement alpha brick acid and put it in the first tube. And then to that, we're going to add calcium hydroxide, which is this white dust. And in we go. So very hot. Next we have sulfuric acid. Very syrupy. And calcium hydroxide again. So here comes the base. Not near as aggressive, but if you feel it, it is getting pretty warm. Next one is phosphoric acid. Also very syrupy. It's like the ring of death over here with all these strong acids. And calcium hydroxide one more time. Nothing too exciting there, although it is getting warm. Two left, we have sulfuric acid, so battery acid coming up. This would be the syrup that would eat your pancake. And now we have potassium hydroxide. These are in pellet form. So let's grab a pellet. Bombs away. Definitely angry there. And last one, phosphoric acid. The other death syrup over here. These are all concentrated acids, very, very dangerous. As you can tell, what they do to bases. Remember, your fingers have amino acids that have bases, so they would definitely react. And then lastly, potassium hydroxide pellet to meet its death again. So again, we are observing those temperatures. So take a few minutes to write in those temperatures. Hopefully your busy work is done. Don't forget to balance your equations. Recognize that not everybody's a precipitate, at least a spectator right on this page. You might have a few precipitates by coincidence, but definitely look for water to circle. See you next time.